Okay, so today we will talk about stabilizer subgroups. Okay, so given a group G, okay, it's a group, and a set X, okay, a set of anything, okay, just random elements, okay, doesn't matter. Okay, now, if you have an element G that belongs to, big G, okay, so G is an element of big G, the group. Now, if the action of G leaves um, x, little x in big X fixed, so it doesn't move it, then we say that G is a stabilizer of the point X. G is a stabilizer of the point X in big X. Okay, cool. Now, in fact, the set of all stabilizers of a point, okay, forms a subgroup. So all what just happened? Okay, all stabilizers of x, little x, okay, of a particular point form a subgroup called the stabilizer subgroup. It forms a subgroup of big G. Okay. Now, um, the trivial stabilizer group means that the only element of G, big G, that um, that leaves whatever point you're talking about uh, fixed is the identity element. So a trivial stabilizer subgroup means that every element actually moves x. It means that means every other element other than by other I mean other than the identity actually moves x, little x and x. Okay, cool. So that is the trivial stabilizer subgroup. That means that the action, we say that the action of G, of all the elements of G, um, on set X, obviously other than the identity, is free. Okay, free. So there's no combination, there's no A and B combination, no A, B combination, where A is in big G and little b is in big X, that leaves B unmoved. Okay, that leaves B unmoved. So B is moved. Okay, unless the identity is unless it's the identity element of a big G. Okay, so we say that the action on X is free. So um, free action, free group action, or acts freely, whatever you want to call it. Okay. Now, if the action of a group G on a set X is free, then, okay, if you take any element of G, not the identity, and act on any element of X, you are going to get a different element. Okay. So um, two, so two elements, two group elements of G, so let's say M and M, will not send the same little x in X to the same Y, okay? So for example, let's say I have 20 elements um, in G, okay, and let's say I have like just X has like whatever, like 500 elements, and like 500 elements. If I take all 20 onto this one, it will go to different ones. Every element of G sends this guy to a different element in X, okay? No overlap. So this is actually used in constructing manifolds, and if you have orbits, orbifolds. They're also used in constructing principal G bundles, which are all the rage nowadays in the Langlands program. Yeah, and that's it.